Okay, so let's start with thermodynamics. So first we will look at some basic terminologies of thermodynamics, what it is and all that. So thermodynamics basically it deals with the moving heat energy. Whenever the heat energy it moves, like heat energy will also call it the thermal energy. When that thermal energy moves, it can do work or a transfer of energy can take place. And that is what we will study in thermodynamics. So the flow of heat energy, it exhibits some special properties, some special principles, some special phenomena, some special laws. That is what we will discuss in thermodynamics. So in order to get to that level, first we have to understand some basic terminologies which we will be using a lot in thermodynamics. So first we have to make ourselves familiar with some basics. Basic terminologies. Let us quickly do this. So we have some interesting concepts. Like we have a concept of system and state and all that. So first we will be discussing what do we mean by system. Thermodynamic system. Thermodynamic system. So what is system? So basically the idea is that we perform an experiment or we observe some event. So the region where we are performing the experiment or the region where we are observing and phenomena and event, that region is known as system. So there are two things, one is the system and one is the surrounding. So let us suppose I have a special region and I'm calling it like system. And all other region apart from this system, that will be the surrounding. Surroundings. Now, how to define this system? Like, what is this system? So this system, this region, basically it is a region of analysis. Like whatever experiment we are performing or whatever phenomena we are observing, we are focusing on this system, this region. So region of analysis, we can say that. And everything other than the system, that is the surrounding. So I can say surrounding as everything external to the system. Everything external to the system. It is the surrounding. Okay. Now this system, I can further break it into three parts. Like we can have three different types of systems, and that is very important. That is what we will discuss now. We have something known as isolated systems. We have something known as isolated systems. Isolated systems. We have something known as closed systems. The region where we will be having an experiment or where we will be analyzing, that region of space can be isolated, it can be closed, or it can be open. Now, what is the difference we will discuss? Or it can be open systems. Now, when I talk about isolated system, here no exchange of energy will take place. The system is completely isolated from the outside world. No exchange of matter, no exchange of energy. So let me write it. So in isolated system, matter and energy, no exchange with the outside world. No interaction with the outside. But in closed system, energy can interact. Matter will not interact. Like matter will be conserved. Matter will, no matter how, it will never go outside. But energy can go outside. And examples also we will look at to get a more good feel of it. So exchange of energy can take place, but no matter. But in open system, both matter and energy exchange can take place. Both matter and energy exchange can take place. So matter exchange. For example, let us suppose I have a closed room wherein I am boiling water. When I will boil the water, water molecules, it will become vapor, and that vapor will try to escape that room, and it will try to get into the surrounding. And also the heat energy will be carried by that particles, and the heat energy will also try to escape from that system. In isolated system, we pack that room in such a way that neither the vapor particles it will be able to escape, nor the energy will be able to escape. So that system, energy might escape. For example, the thermos we use to keep water hot or to keep the tea hot. Definitely no exchange of matter is taking place because the thermos we tightly pack it. So there is no opening and hence no exchange of matter. Matter can never escape from that thermos, that's closed system. But energy can exchange because after some time you will see that the hot tea it became cold. It happens. So loss of energy is continuously taking place, and that is the closed system. But in isolated system, change in internal energy will be zero. All that we will discuss in detail. But now we got a feel of it. And it is so important that whenever we are discussing any phenomena in the thermodynamics, we specify the system because for every system, the same phenomena will behave differently. And in open system, like the real world which we live, like the kitchen is an open system where continuously the vapors they are escaping to the surrounding with the energy also. Energy also they are carrying with themselves. So that is an open system. So three systems we got to know. Similarly, we have some special properties of the system. Like properties of the system, we can classify it into two types. Let us look into that. So when I talk about properties of system, it can be intensive property or extensive property. What it means, we will look at properties of system. So we can have intensive properties, so intensive properties means they do not depend on the amount of matter. Do not depend on the amount of matter. And what is amount of matter? Mass. Do not depend on the amount of matter in a sample. Or in a system. Now, what it means? It means that regardless of whatever the matter is, we can increase the matter, we can decrease the matter, these properties will remain same. These properties, intensive properties, will never get influenced by the amount of matter. Intensive properties are independent of the amount of matter. Now, what are those intensive properties? One very interesting example of that intensive property is the temperature. No matter how much, how many people get inside a room, the temperature will be as it is. Now, it will not get influenced. Or no matter how many things you add inside a room, like if you keep on increasing the amount of matter or keep on decreasing the amount of matter, temperature is what it is, room temperature. At every point, it will be like a value we will get. So temperature is an intensive property. It is independent of the amount of matter or the mass. And similarly, we have boiling point. See, boiling point of water is 100 degrees Celsius. Now, no matter if you boil 1 liter of water or you boil 100 liters of water, it will not matter. Like I have a very big container, and if I try to boil 100 liter of water, and I feel that, oh, since I'm boiling 100 liter of water, the boiling point might increase, but it doesn't happen. So regardless of you boil 100 gram or 100 liter, boiling point will remain same. So that is the intensive property. Similarly, we have something called as extensive properties. So definitely extensive properties will be the reverse of intensive properties, meaning to say that they will depend on amount of matter in a sample. Dependent on the amount of matter. Dependent on the amount of matter. In a sample. So this is the extensive property. So now we got a very good understanding about Intensive property, extensive property. Let us look at some example of extensive property to get more good, like clear idea. So we have something called as weight. Let me write it. See, the formula of the weight is mg, and hence weight is dependent on the amount of matter. If we keep on increasing the mass, the weight will keep on increasing because the gravity, the acceleration due to gravity, that will keep on increasing. Like that is constant, but like m into g, the gravitational force, that will keep on increasing. So weight is dependent on the mass and length. Now we have to digest like how length is an extensive property. And it's very easy to understand. If I keep on increasing the amount of matter, that amount of matter keep on occupying more and more free space. And hence the length in all the directions will keep on increasing and its volume will keep on increasing. So length is dependent on the amount of matter. If the amount of matter is very small, less, then length will be small. So now this basic idea we got. So now until now we saw that okay, thermodynamic system is like the first terminology which we are discussing. Let me write it like first terminology. That is a thermodynamic system. And we saw that okay, system is the point of analysis, region of analysis. Surrounding is everything other than that. We can have an isolated system, closed system, or open system. Isolated system, no exchange of energy, no exchange of matter. Closed system, exchange of energy will take place. Open system, both exchange of energy and exchange of matter will take place. Every system, when we will be analyzing it, we will be measuring some properties of that system. So properties of the system can be intensive properties or extensive properties. Like properties which depend on the amount of matter, that is the temperature and boiling point. No, does not depend on the amount of matter, temperature and boiling point. And properties, extensive properties which depend on the amount of matter, that is weight and length. Now we will look into the next property, like next terminology of thermodynamics, basic terminology, that we will discuss. That is the state function. State function. So this is the second property we're interested in. Like not the property, but the terminology. Second terminology. That is a state function. So the idea is that what do we mean by state function? State function means that it depends only on the state, like initial state, final state. It is independent of the path. So let me write some properties of this. So when I talk about state function, depends only on the initial state and final state. Depends only on the initial state and final state. Depends only on the initial state and final state. State function. State function is independent of the path. independent of the path used to reach from that initial state to final state. And examples are very important. Like let us. So this temperature, it is a state function. The temperature is a state function. Like in temperature, we are only interested in the current temperature or the initial temperature and final temperature. We are not at all interested how we achieve that temperature. We are only interested in the value of the temperature. We say that, okay, what is the value of that temperature? How we achieve that temperature? Why is it so? Because no loss of energy is involved here. Regardless of whatever method you apply, I will always get the fixed value of temperature. And pressure is also one example of a state function. Internal energy is also a state function. Internal energy of the system, it is a state function. Enthalpy is also a state function. Enthalpy is also a state. So these are like some examples of state functions. Temperature, pressure, internal energy, enthalpy. Meaning to say that we are only interested in the initial value and the final value. We are not at all interested, like their values are independent of the path used. No matter how you increase the pressure, what was the pressure 5 minutes ago, what is the pressure 5 minutes afterwards. We are interested in the values. So we can draw one graph for the state function. Let us draw one graph. So in the x-axis, I have the volume. That is the capital V, I can call it. And in the y-axis, I have pressure. That I can call it. It is increasing in that direction. Now the idea is that I have 2 points, 1 and 2. At any particular pressure, there is a volume. Now I can go from state 1 to state 2 using this path. And let us suppose this is the path. And I can go from 2 to 1, like from this state to this state using path. Now in both the path which I follow or which I adopt, internal energy will change. Now interestingly, this change in internal energy will be same for both the path because the points are same for both. Like in the first scenario, I am going from 1 to 2, and in second scenario, I am going from 2 to 1. So the magnitude will be same for both. Like delta U will be same, regardless of the path, because we are using different path. Regardless of the path, delta U will be same. The magnitude of change in internal energy will be same. It clearly shows that internal energy is a state function. So this is an experiment. Experimentally, we found this kind of a nature exhibit. And hence we say that all these thermodynamic properties, which we will be discussing, like the properties of the system, which we will be using a lot. Because in thermodynamics, we have a system with these parameters, and we will changing these parameters, and we will be deriving some equations like how that thermodynamic system gets affected with this. All that we have to discuss. But now, okay, state function is clear to us. Now we will discuss something more interesting. That is the path function. Now, definitely, we are getting an idea that, okay, path functions should be something which might depend on the path. Let us see. The third terminology which we are discussing, that is the path function. So, this path function, it depends on the path. Depends on the path between the initial and final state. Initial and final state. Okay. This is the path. For example, work done. Work done is a path function, and heat transfer is a path function. Now we will get a feel of it why it's a path function. So see, basically, in this both the aspects, energy is involved. Like if I talk about work done, in order to do any work, energy is needed. Like I can give you one example. I have to go from point A to point B. One of the road is smooth, no potholes, nothing. It's very smooth. And another road, it is full of ups and downs, like very harsh road it is. So definitely amount of energy needed, like work done in moving from A to B will be less. It is obvious. You can, and here I have to apply more effort, more work needs to be done. Which means to say that, or let us suppose I have one more smooth road, but in which I have to travel more. Then you will say that, oh, we have studied work done is equal to force into displacement. So regardless of whatever path I will choose, displacement should be same. So work done should be same for both the path. But in reality, like work energy theorem, also we have seen that whenever work done is involved, energy is involved. We have to put effort. In chemistry, we discuss from this aspect. Any chemical process we do, energy is involved in there. We have to apply work. So work done is a path function. It depends on the initial path and final, like initial state and final state. Okay. And similarly, heat transfer. Heat transfer is also one like path. Now, next property we will discuss, like next terminology, that is the internal energy. Like internal energy, in many of the formulas we will use internal energy. Internal energy. And we can represent this internal energy with capital U. So capital U stands for internal energy. And very important formula I'm writing. So basically, internal energy is equal to kinetic energy plus potential energy. So internal energy of a system is the sum of kinetic energy plus potential energy. Or in short, I can say that the total energy of the system is the internal energy. So next property we can, so internal energy, it's a state function which we already saw. It is independent of the path. It's a state function. It depends only on the initial state and final state. So state function, internal energy, and it is an extensive property. Extensive property means it depends on the amount of matter. And it is understood if there is more matter present, then those particles will be containing some energy. So internal energy will increase. Something like that. Extensive property. For example, I can prove that internal energy is an extensive property. I have a container. I have a container which is containing some gas particles. If it is containing less gas particles, then definitely the total energy or the internal energy of the system will be less, because every particle, gas particle, is moving and it is having some kinetic energy. That is the kinetic theory of gas. If I increase the particles, if I increase the concentration of gas, then definitely the internal energy of the system will increase. So the internal energy of the system is dependent on the amount of matter, and it's an extensive property. Now, one more very important property we will discuss about internal energy. Like it's important property. See, this internal energy, energy transfer, energy transfer leads to change in internal energy. Energy transfer leads to change in internal energy. And it is understood. energy transfer means whenever there is a transfer of energy, like in a system, if we heat means we supply additional energy, then internal energy will increase. Or if system does any work, then its energy is lost. So internal energy will decrease. So whenever energy transfer I'm talking about, this energy transfer can be via heat or via work. So in thermodynamics, there are two ways through which energy transfer can take place. Like a system is having good amount of energy. Now, if it wants to release that energy, it can release it via heat. And all these systems, like the system in which we live, energy transferred through heat is so common. Like we have a hot tea, after some time it becomes cool. So energy transfer is taking place via heat energy. And these systems, they can also transfer their energy via work. They can do some work. Like if I have a piston, so the gas, it can do a work to compress that piston or expand that piston. So if it is doing a work, then energy transfer is taking place. So energy transfer in a system always takes place either via transfer of heat or either via doing some work. And whenever energy transfer takes place, internal energy of the system will decrease for sure. Not decrease, but change for sure. It can decrease also, it can increase also. It depends. So I can say that change in internal energy of the system, it is equal to final energy minus initial energy. Final state minus initial state. So that is what is change in internal energy is. Now one more terminology we can discuss now. We have time left. So that is the state of a system. State of a so the state of the system. It is so the state is basically it is described by some thermodynamic variables. So the state of a system is described by some thermodynamic variables. Like thermodynamic variables, like temperature, pressure, all that. So we have temperature, pressure, temperature, pressure, volume. These are the state of the, so like these variables describe the state. So whenever I talk about the state of the system, I check, okay, this is the system, what is the temperature, what is the pressure, what is the volume, and some special composition if it is having, what is the system composed of, the composition of the system, and so on. And change of state, when a change of state occurs, when these variables change. So a system can be in one state wherein it has a specific temperature, pressure, volume, composition. And due to some external factor, or these variables can keep on changing, and hence the state of the system can keep on changing. The change of state. When one or more of above variable undergo change. When one or more of above variable undergo change, then we say that okay, change of state of system occurred. Now here four very important things we should know, very important things. In terms of change, we can have adiabatic change, like we can have adiabatic, all of that we will discuss in some detail. Adiabatic. Then we have isothermal. So we say that adiabatic process, isothermal process, isobaric, and we have something called as isoporic. So a process, a thermodynamic process in which no heat transfer is taking place. No heat transfer if it is taking place. Then that is adiabatic process. Mathematically, we can represent adiabatic process as delta Q is equal to 0. Like change in heat energy should be 0 because no heat transfer take place in adiabatic process. Delta Q should be equal to for adiabatic process. Similarly, we have isothermal process. In isothermal process, what happens? Uh, constant temperature. Constant temperature. Constant temperature means delta T should be 0. The change in temperature should be 0 because constant temperature. So in isothermal process, always delta T is 0. In isobaric, constant pressure. Isobaric means constant pressure. Meaning to say that delta P is 0. Isoporic, constant volume. So delta V is zero. The change in volume should be. So now this is so important and so interesting that sometimes in the numericals, the nature of the process is given. It is given that in an isoporic process, this and this and this happened. And we have to make use of these basic observations. Okay, if it is isoporic, then I can use delta V is equal to zero. Or it is isothermal, I can use delta T is equal to zero. Or the process is adiabatic, I can use delta Q is equal to zero. Or the process is isobaric, I can use delta P is equal to zero. So this uh, can be very useful. So today I think we can keep till here.
Yes.
Just